We are Team Delta V, and this is our submission for the International Space Challenge ISC 2025. Our team consists of three members, Jeeval Shah, Xiao Xiang, aka Lucas, and myself, Ishita Agrawal. This is what we'll be covering today. It includes an overview of the chosen mission and the AI suggestion, implementation techniques and guidelines, budget and regulatory considerations. Our goal as a team is to propose an AI improvement to a pre-existing space mission that would increase operational efficiency and enhance scientific output. First, the introduction. Our main objective of this pitch deck is to map Hubble's operations constraints, to identify leverage points for improvement, propose the possible AI interventions, the specifications of its implementation, and quantify the results of doing so. That leads us to our primary idea of a dual-layer AI co-pilot system for the Hubble Space Telescope that runs in a parallel to the operational system to predict faults and clean up images. My teammate Jeeval Shah will be taking you through the next part.
Hello, so I'm Jeeval Shah and I'll be talking about the literature review. So we've referred to quite a few papers to build our proposal, but we felt that these two were the most relevant. So the first one is AI-based technologies for International Space Station, and it essentially discusses how AI-enabled robonauts can help astronauts do their manual work, and it can also help in autonomous satellite missions and predictive maintenance. The second paper is transformer-based anomaly detection for satellite telemetry data. This paper makes use of a transformer-based model to detect anomalies in satellite telemetry data, and this allows them to have a very fast throughput and detect faults very accurately and quickly. Next, I'll be talking about the AI-enhanced solution that we propose. So our solution has a dual-layer architecture. First, there's an onboard AGI over the satellite, and then there's a ground-based AI, which will be used for powerful model training and the updates. On board, the AI system will monitor the gyroscope, the wheel torque, which is used to orient the space telescope, the temperature, and the power. It will try to predict faults early using pattern learning and try to keep false alarms to a minimum. Furthermore, it will clean images and remove noise and artifacts. The ground AI hubs will be used to train massive models on historical data, and it will also be used to compress and upload these optimized models to the satellite system. Now we move on to the data, testing, and hardware. So data we use is the real telemetry data, but what we will do is add faults synthetically and simulate these faults to cover a wide range of scenarios so our model is prepared for a whole range of scenarios it may encounter. Furthermore, we'll use temporal transformers as we discussed about the paper earlier, which will allow us to detect anomalies over a period of time steps. And we also plan on using CNNs to help better image quality. For the testing part, we plan on using Monte Carlo simulations, which will allow us to explore different fault scenarios and be able to carry out different simulations. The shadow mode will validate the safety of the model before deployment, and the human in the loop will ensure that the real-time performance is up to the mark. The hardware we plan on using is lightweight. It has to be radiation tolerant, and it may or may not have an accelerator. We plan on using optimized models that run efficiently within power and memory limits, and the AI will run in advisory mode without direct control. Next, we move on to the analysis and results. So here, the baseline we have talked about is the rule-based safe mode, where the human is in the loop and makes all the decisions, whereas our proposed solution will have fault detection and onboard imagery cleanup. Our AI system will be advisory first, but it may have limited auto actions in non-critical scenarios. For evaluation and setup, as discussed earlier, we'll be using real telemetry data with injected synthetic faults. The key performance indicators will be the fault detection latency, how long it takes to detect faults, the true positive rate, the false alarm rate, the compute load, it has to be kept under a threshold, and the model update latency, how long it takes to update the models. Now, I'll be handing it over to Ishita, who will be talking about the ethical frameworks.
Our proposal pillars around the key concept of AI recommends, human decides. We want our AI to act as an assistant to the current operations of the Hubble Space Telescope rather than a replacement. We ensure this in the following ways. For the action of fault detection and maintenance that we hope to achieve through the use of AI by implementing the fundamental concept of statistical hypothesis testing, we aim to come to a conservative threshold between a type 1 error, where null hypothesis is incorrectly rejected, leading to a false positive, and a type 2 error, where a false null hypothesis is not rejected, leading to a false negative. This threshold decides how big the fault needs to be for it to be flagged. But it is important to note that ultimately it will be the humans making the decision on whether to carry forward with the maintenance or not. This is to ensure that resources aren't being wasted on unnecessary repairs and that crucial repairs are not blindsided by the system's failure to recognize them as such. For the action of image enhancement, we would need to make sure that the AI does not create imaginary output and only works on clarifying the image. On the other hand, it should also not erase important information. Thus, raw data should always be preserved and be accessible. Overall, these ethical and regulatory considerations have been put into place upon assessing the telescope's architecture and balancing out the costs and benefits of implementing AI, which will be discussed in detail in the next section by my teammate Lucas.
And so now I will be talking about the budget for our mission. Here's the budget required to execute and validate our onboard AI solution. We structured it to include all essential hardware, sensors, and testing tools needed to build a fully functional development environment. The compute development board serves as the system's main processing unit, while a USB NPU accelerator enhances real-time AI inference performance. For data acquisition and monitoring, we've included gyroscope and temperature sensors, as well as current and voltage monitors. A key component of our setup is the reaction wheel motor, which allows us to simulate spacecraft dynamics and test predictive maintenance algorithms without requiring actual space hardware. A bench power supply provides a stable and adjustable power source to test system performance under different conditions. We've also allocated budget for storage devices, input or output tools, and data acquisition equipment to support data logging and interface testing. In addition to the one-time hardware expenses, which is about $2,120, we also factored in recurring cloud storage costs, which is around $72 per year, to support large simulation datasets and continuous AI model training. Lastly, a 10% contingency, which is about $220, covers unexpected costs such as accessories, shipping, or replacements. In total, the project's budget is approximately $2,352, which we believe is a cost-effective plan to deliver a robust and testable AI-enabled spacecraft system. Lastly, I'll talk about the conclusion. Throughout this project, we demonstrated how implementing artificial intelligence in the Hubble Space Telescope's operations can significantly enhance its performance, reliability, and scientific output. We propose a dual-layer system that combines onboard predictive maintenance and real-time image enhancement with ground-based model training. This approach directly addresses key challenges such as delayed anomaly detection, bandwidth inefficiency, and heavy human dependency. With our solution, Hubble can extend its operational lifetime, respond more effectively to potential faults, and process scientific data more intelligently. Ultimately, this allows the telescope to generate more mission data and deliver higher quality results to researchers. Thank you.